Welcome to today's deep dive. We are exploring Timothy J. Dillon's manuscript, OmegaGenesis, and looking at how tackling a century-old math puzzle accidentally created a commercial software blueprint for governing AI.
Yeah, it is a truly fascinating leap from abstract theory to practical application.
Okay, let's unpack this. You are likely already familiar with the Collatz conjecture, right? The classic 3n plus 1 loop.
Right, the one that has basically baffled mathematicians for decades.
Exactly. You take a number. If it is odd, you multiply by 3 and add 1. If it is even, you divide by 2. And we know it sends integers into these endless, chaotic spirals.
And for nearly a century, people have basically just been chasing those infinite trajectories using, well, traditional heuristic approaches.
Which completely fail to capture any rigid constraints.
Right. But Dillon introduces a massive paradigm shift here. Instead of chasing infinity, the OmegaGenesis program uses a geometric lens. They call it two-adic valuation depth.
Let's pause there because two-adic valuation depth sounds incredibly dense. What does that actually mean in practice?
So think of it like looking at a tangled ball of yarn through an X-ray. Suddenly, instead of a chaotic mess, you see the rigid geometric structure underneath.
So it compresses the dynamics.
Yes, it traps the mathematical chaos into a rigorously bounded, testable framework. He basically stops looking at the infinite wilderness and starts looking at the underlying geometry.
And by applying that specific X-ray lens, the paper forces any of that non-convergent chaotic behavior into 4 highly specific residual families. The manuscript labels these S, R, H, and C.
Exactly. It takes this theoretically infinite search space and aggressively prunes it down. It isolates what Dillon calls a finite near-critical core.
So he literally takes infinity and boxes it into something manageable.
Yes, and that brings us to the really thrilling computational evidence. They stress-tested this near-critical core using exact arithmetic up to a modulus of 3072.
Which basically means they were testing incredibly massive numbers to see if any could escape the box.
Spot on. When they ran the numbers through the protocol, it spit out exactly 730 potential core candidates. But here is the kicker. After applying Dillon's mathematical filters...
Wait, let me guess.
Exactly. 0 survivors remained.
Wait, 0 out of all 730?
0. 250 were eliminated because they failed exact divisibility rules, and the remaining 480 failed to even be positive odd integers.
So the mathematical system's so-called danger zone is completely empty.
Completely empty.
So he proved this danger zone is empty, but he didn't stop at an academic proof, did he? And this is where it connects directly back to you, the listener.
Right, because why should you care about abstract arithmetic and eliminated odd integers?
Exactly, because this theoretical architecture didn't just stay on paper. It was directly translated into real-world enterprise software called the Omega Stack.
Right. We connect this to the bigger picture. Modern digital environments act just like that math problem. Think about AI agents, financial transaction pathways, or cybersecurity networks.
They make millions of branching decisions.
Exactly. They evolve through feedback and repeated state transitions, very much like the Collatz map.
So if an AI agent is trying to solve a problem and gets caught in a loop, it is essentially acting like a rogue Collatz sequence.
Precisely. If one branch loops out of control, the whole system crashes. That raises the critical question of how we actually govern that digital chaos.
And the exact mathematical constraints used to tame the Collatz conjecture now power the OmegaGenesis engine.
Right. It is applying those geometric boundaries to digital networks. The engine monitors structural instability in these complex systems.
Because it relies on Dillon's deterministic framework.
Yes, so it can predict those infinite loops and actually throttle or hard stop rogue digital processes before they spiral out of control.
It is amazing to think that the Collatz conjecture has been viewed as basically just an academic anomaly since the 1930s.
And now it is providing the precise architecture to keep artificial intelligence from going off the rails.
Exactly. And it leaves you with a really provocative thought to explore on your own.
Oh, absolutely.
If an unsolved math puzzle from nearly a century ago holds the exact structural intelligence needed to control modern AI...
What else is out there?
Right. What other abstract equations currently sitting unproven in textbooks might be the hidden keys we need to govern the unforeseen technologies of tomorrow?